We started. We are now recording, so you can go ahead when you want.
Thank you.
Thank you.
Hello, everybody. Thank you for coming here for this special seminar. The talker is Elias Kyritsis. He's a student, a PhD student in the University of Crete, the same university where he got his bachelor in physics, his master in advanced physics with specialization in astronomy. And he's now, as a PhD, as I said, with the supervisor of Andreas Zezas, who is also here. And actually, it's the supervisor of it's my and Maria's supervisor from the University of Crete. It's very nice to have both of them here. And it's also very nice to have Elias here for me, because aside from the scientific value of his work and for me, there's also some sentimental value. And this is the first time I tell him that, because as a PhD student, I worked on something that's very mundane for some of you, you may know, to create a galaxy catalog, a value-added galaxy catalog, and it took 3 years to finish it. Multiple galaxy catalogs, match the data, derive properties. So it's a very complicated business. And then life happens. You go for a postdoc, you leave it, and you say that if there's not someone that's going to take it and continue it, which needs someone that has a lot of courage to get in the dirty data of astronomy and extragalactic astronomy, then it's gonna die. And I was leaving, and then I heard that Elias was there, continuing the project. So for me, it's something very important that there is someone that can deal with the complexity of such a project, can continue it, and expand it and enhance it. So I'm very glad that I see now this expansion, these new works from Elias here. So Elias, the floor is yours. And
good morning, everybody. Thank you, Constantina, for the very nice introduction. I didn't expect it. So today I'm going to talk to you about my work on the X-ray emission of normal galaxies, and how it is connected with the stellar population characteristics of these galaxies. But I would like first to start with a short introduction. As you may know, the X-ray emission of normal galaxies is produced by X-ray binaries and hot gas. X-ray binaries are binary systems which are comprised of a compact object, usually neutron star or a black hole, which accretes matter from a companion star. Based on the mass of the companion star, these systems can be further classified as high-mass X-ray binary systems or low-mass X-ray binaries. Hot gas is the diffuse X-ray emission of hot ionized gas, which is the cumulative effect of stellar winds and supernovae. Why is it important to study X-ray binaries? First of all, X-ray binaries is an easily observable phase of the evolution of some binary systems. Furthermore, by studying these systems, we can constrain the initial parameters of XRBs, like orbital parameters or mass ratios, and also their evolutionary parameters like stellar winds, supernova kicks, and common envelope, by testing different evolution scenarios through population synthesis codes. Some of these systems, X-ray binaries, depending on the evolutionary path that they will follow, can end it up as a gravitational wave source or short gamma ray bursts. For that reason, by studying XRBs, we can predict the formation of such very, very interesting sources. In addition, by studying the X-ray binaries, we can set constraints and understand the effect of X-ray binaries on their host galaxy and their surrounding intergalactic medium. A very useful tool and powerful tool to study all these things is by studying the correlation of the X-ray output of these galaxies with the stellar of these binaries with the stellar population parameters of the host galaxy, like star formation rate, stellar mass, and metallicity. But X-ray binaries are not only important for local universe studies, they have also important implications in cosmological studies. For example, by studying these systems, we can set constraints on the evolution of compact objects populations. All of us, we know the very famous plot for Maddow and Dickinson, which shows that the peak of star formation rate of star formation history is about 2 redshift of 2. And at these higher redshifts, we expect the formation of more high mass X-ray binary systems. Furthermore, by studying the X-ray binaries, we can also set constraints on the cosmological evolution of galaxies. There are theoretical works that show that in the very high redshift universe, before the epoch of reionization, the dominant population was the high mass X-ray binaries. And as a result, these systems may affect the formation of the first galaxies in the universe. The last 20 years, a significantly larger number of works have tried to study the X-ray output of normal galaxies as a function of the star formation rate or the specific star formation rate, which essentially is the star formation rate per stellar mass. And it's a measure of the intensity of the star formation in a galaxy. And also the metallicity. These works have shown that there is a correlation between the increased X-ray luminosity with the metallicity, and recently Gilbertson et al. Saw that there is a correlation of the X-ray luminosity, of the increased X-ray luminosity with the age of the stellar populations that belong to the host galaxy. However, all these studies so far are based on limited and non-representative samples. That means that all the scaling relations derived from these studies cover a small fraction of the parameter space of the star formation rate, stellar mass, and metallicity. In order to set better constraints and improve these scaling relations, we need larger statistically significant galaxy samples. And there is no better catalog to use than the Heraklion Extragalactic Catalog, which is a value-added catalog built by your own Konstantinos Kovlakas. And this catalog includes all the galaxies within a distance of 200 megaparsec and provides basic properties about their position of the galaxies, their distance, their size, multi-wavelength data, photometric and spectroscopic, stellar population parameters, star formation rate, stellar mass, metallicities, and activity classification. However, the completeness of the first and the publicly available version of Hecate is limited by the available photometric information for the calculation of the star formation rates and the stellar masses, and by the available spectroscopic information for the calculation of the metallicity and the activity classification of the galaxies included in the Hecate. For that reason, I'm working on the development of the Hecate version 2. And here you can see the ice of Hecate in the multi-wavelength sky, which includes information from the first version and for the updated version 2 that I'm working now. As you can see, the updated version of Hecate provides photometrical data from optical to far infrared. And we also include photometric optical data from Pan-STAR survey. So in the new version, we cover a large fraction of the sky. And based on this, updated information, we recalculated the stellar population parameters. For example, for the stellar mass, we used the near-infrared, mid-infrared photometric data. And as you can see, we managed to increase the available information up to 90% for the stellar masses. Same for the star formation rate up to 65%. And for the metallicity, since we have the available information for the stellar mass, based on the mass metallicity relation, we managed to have metallicities in the updated version of Hecate for the 90% of the galaxies included in the catalog. Sorry. So, as I mentioned before, the Hecate, the first version of Hecate provides activity classifications. But the number of galaxies which have available classification is limited by the spectroscopic data. For that reason, in order to increase the completeness of the activity classification in the updated version of Hecate, Haralambos Daoutis, who is now a PhD student of Andreas in University of Crete in the Institute of Astrophysics, developed a new classifier which is based on optical and infrared colors and on machine learning methods in order to classify galaxies based on their activity. As we saw, one of the problems of the standard methods, which one is the emission lines, the spectroscopic classification methods, is that they require spectra and they are applicable only to emission line objects. That means that spectroscopic methods lose a population of passive galaxies which do not show emission lines. In addition, other traditional methods like ICD are subject to degeneracies, and their results depend on the AGN templates that we consider. Finally, the infrared multiband photometry diagnostics are promising, but they have a limitation. They miss the majority of low luminosity AGN. As you can see here in this plot, we have the two diagnostics from Asef and Matteo based on mid-infrared colors. In this region here is the AGN locus, and here is all the other galaxies. And the green colors, the green dots, are spectroscopically confirmed AGN, which do not fall in the AGN locus defined by the mid-infrared colors. So for that reason, Babis, Haralambos Daoutis tried to develop another classifier applicable to larger samples with improved efficiency. In order to do that, he built a training sample based on spectroscopic classification of active and passive galaxies. In particular, by using the MPE Johns Hopkins University spectra catalog of galaxies, we applied the 4D emission line ratio diagnostic of Staboulis, and we get the labels for emission line galaxies like star-forming AGN, composite, and liners. But not only that, by using the same spectra and selecting only those that lack emission lines, we defined a new class of passive galaxies. The photometric data that we used are based on mid-infrared and optical colors, and the final combination of features that we fed in our model is these three colors: two from the WISE or all-WISE survey, mid-infrared, and one of the optical. By using these features and these labels, we trained a random forest classifier for a sample of almost 41,000 galaxies. And here you can see the performance of our model in the form of a confusion matrix, where we have the predicted class here and the true class on the y-axis. As you can see, our model gets an excellent performance for star-forming galaxies and passive galaxies, has moderate performances for AGN, liner, and composite galaxies, And as we found, the performance of AGN is increased with the distance of the galaxies. And since we had this new activity diagnostic, we applied it to the Hecate catalog. And here you can see the result of this application. We have again the same plot with the mid-infrared diagnostics. And the different colors indicate the different classes predicted by the new activity classifier. And the very interesting thing is that, first of all, the new classifier managed to classify the missing subpopulation of AGNs. Here, you can see that all these dots are classified as AGNs. But something which is very important for my work, and what I will show later, is that it managed to find very extreme star-forming galaxies, which would classify by the old diagnostics as AGN. Are these two blue dots there? So now that we have the updated version of Hecate and we have all the galaxies in the nearby universe, what we need is the X-ray data. And the X-ray data are coming from the eROSITA survey, which the eROSITA telescope launched in 2019, and its plan is to scan the entire sky 8 times. eROSITA survey is the first all-sky survey above the 2 keV energy band, and the most sensitive below the 2 keV. And as you can see here, we expect to detect orders of magnitudes more galaxies with the ERAS survey than all the previous studies. So by combining the updated version of the Hecate catalog with the ERAS-1 survey, we managed to construct a parent sample, to build a parent sample that includes all the Hecate galaxies which are in the ERAS-1 sky. And the number of these galaxies is almost 94,000. For all these galaxies, we performed X-ray photometry by measuring the integrated X-ray photometry, integrated X-ray emission within the galaxies D25. I would like to emphasize here that for the analysis, for the X-ray analysis, we didn't run a detection algorithm in order to select only the detections. Instead, we used all the emission which is within the D25. And for that reason, our sample has not only bright X-ray sources, but also faint X-ray sources. And for that reason, in order to measure correctly the X-ray flux, we used a Bayesian approach where we calculated the posterior probability of the source intensity. And here you can see two characteristic examples of our sources. This is a bright source, and you can see the shape of the posterior count distribution. And this is a source with a very low number of counts. You can consider that in the slides later as a detection or an upper limit. Based on these distributions, we calculate the flux and the luminosity by using the distance of each galaxy. As I mentioned, it's very, very important and crucial for this kind of work to select the most bona fide star-forming galaxies that we have available. For that reason, we used two activity classification methods, the standard one, which is based on spectroscopic data, and the photometric classifier that we developed with Haralambos Daoutis. Because both of these methods are probabilistic in the sense that they give a probability distribution of a galaxy to belong in its class, we set a lower limit on the galaxies that we select as star-forming, and we only chose those that have probability to be star-forming higher than 75%. Now, because we use two different activity classification methods, we also checked the AGN contamination in our sample based on the different classifications. And we found that the maximum AGN classification based on the method that we used is 3%, so it's negligible. Furthermore, we checked a reasonable, a large sample of our galaxies by visual inspection in order to be sure that we don't have AGN contaminations, but also we exclude galaxies from our sample which have associations with galaxy clusters or compact galaxy groups catalogs. Furthermore, we exclude objects that show ultraviolet, optical, and infrared variability because this could be an indication of the presence of an AGN in our galaxies. And finally, we also remove objects that showed hard X-ray colors, which is another indication of the presence of an AGN. After applying all these stringent activity criteria, we ended up with a sample of almost 18,700 star-forming galaxies, and 75 of them are, let's say, detections, but all the rest are upper limits. By using this final sample, you can see that we are orders of magnitudes, we have orders of magnitudes more star-forming galaxies than all the previous studies. And in that way, we have the first unbiased X-ray sample of star-forming galaxies in the local universe. And here you can see the distribution of our sample in the parameter space that we work. We have the main sequence plot, star formation rate, stellar mass, and this is the main sequence line of star-forming galaxies. And as you can see, our sample is well distributed in the star formation rate and stellar mass plane by covering almost 4 decks in both star formation rate and stellar mass. In addition, the color code here indicates the distance of the galaxies. In that plot, we have the same main sequence, but this time color-coded with the metallicity. And as you can see, our sample, it covers a wide range of subsolar to supersolar metallicities. As I mentioned in the beginning, the X-ray output of normal galaxies is X-ray binaries and hot gas. Because we measure the integrated X-ray emission, so we account for everything within the D25 region of a galaxy, here we measure how much is the contribution of the hot gas in the average spectrum, X-ray spectrum, of all the star-forming galaxies in our sample. To do that, we stacked all the available spectra of the 18,000 galaxies, and we fitted our X-ray spectrum by accounting for the X-ray binaries component and the hot gas. And we found that the contribution on the average population of star-forming galaxies is almost 13%, which is not very high in order to affect our results. Another very important thing is that we didn't find any indication of the presence of iron K alpha line, which is a good indication for an AGN, for the presence of AGN. So we can say that our sample is fairly clean of obscured AGNs. And here you can see the distribution of our sample in the X-ray luminosity star formation rate plane, and in the LX per star formation rate in the specific star formation rate plane. The black stars are the detections, and the gray down arrows are the upper limits of our sample. The first thing that we saw, it was very surprisingly when we did the analysis, was that there is a population of extreme X-ray luminous galaxies which is systematically above the standard scaling relations from Mineo and Limel. And another thing is that there is an increased scatter in our population going towards lower star formation rate. But there is a caveat here. Our sample is dominated by upper limits. So which is the solution on that problem? The solution, it has a name, and that name is stacking. So we divided our sample in SFR, stellar mass, and distance bins here, and we stacked the X-ray spectra of all the galaxies included in each bin, and afterwards we measured the average X-ray luminosity of the galaxy population per bin. And here you can see the distribution of the stacked data, the blue boxes. But one reasonable question is how the individual galaxies in each, how an individual galaxy in each of those SFR stellar mass distance bins affect the average stacked signal. To answer that, we performed a bootstrap analysis by repeating the stacking analysis for 100 bootstrapped samples of individual galaxies in each of these bins. And here you see the result of this analysis, where we have the blue population is the stacked data, the average population of galaxies, and the blue shaded region is the result of the bootstrapping analysis. What we saw here, what we find here is that the average population of galaxies is closer to the relation to the standard scaling relations as we would expect, but still the excess in the lower star formation rates exists. And it's stronger towards lower star formation rates and also towards higher specific star formation rates. In addition, the bootstrap analysis indicates that this excess is not due to statistical fluctuations of the populations that participate in each of our star formation rate stellar mass distance bins. And here we quantified this excess by measuring the excess of our average galaxy population in the form of the bins that I described, from the Mineo scaling relation. And you can see that the excess is up to 2 decs for star formation rates lower than 0.01 solar mass per year, and is consistent for higher star formation rate with Mineo. The red error bars here indicate the bootstrapping errors. In addition, we also see that the scatters indeed correlates with the star formation rate. As we go towards to lower SFRs, the scatter increases. As we saw in the introduction, there is a correlation between the X-ray luminosity of galaxies, the star formation rate, and the metallicity of the galaxy populations. To check how is this correlation is in our sample, we plotted the X-ray luminosity as a function of star formation rate and metallicity, and you can see that our sample confirms the anti-correlation with the metallicity. As we go to lower metallicities, subsolar, the X-ray luminosity output of the galaxies, either of the individuals or of the average population of galaxies, is increased. And you can see that the average X-ray luminosity excess is almost 2.5 decs above all the previous scaling relations and also theoretical works. And another thing, since that we found that the scatter correlates with the star formation rate, we thought that maybe there is a correlation of the scatter with the metallicity. However, we didn't find any such indication, since, as you can see, the average the scatter of the average population of galaxies is more or less similar and constant across all the range of metallicities. So now that we have the most updated sample of normal galaxies in our local universe, we updated the X-ray scaling relations. This is the black line with the orange shaded region are our best fits in the LX as a function of star formation rate scaling relation, and the scaling relation of X-ray luminosity per star formation rate and metallicity. And our fit, we used the MCMC fit on the stack data, on the average population of galaxies, accounting for the upper limits and the dependence of the star formation rate with the dependence of the scatter with the star formation rate. And here are the best fit results for our updated scaling relations. But we saw that also the population, the stellar population age may affect the X-ray output of galaxies. To test that, we used an age indicator, which is the ratio of helium-1 to H-alpha emission line, which is a good age indicator because helium-1 line traces young stellar populations with ages lower than 8 megayears, and H-alpha traces slightly older stellar populations with ages lower than 30 megayears. The color code here is the value of that age indicator. And as you can see, we find that indeed there is a correlation between the X-ray luminosity and the stellar population age. For example, if we see, if we fixed at a specific star formation rate, we see that as we go upper in higher luminosities, the gradient in the age indicator is stronger, and that means that in the population dominated by younger stellar populations. The higher this value, the younger the stellar populations that we have in each of our bits. And indeed, the excess correlates with the stellar population of our average population in each of galaxies in each SFR stellar mass B. But the question is, we saw that the X-ray luminosity, the excess that we observed, is correlated with the metallicity, but at the same time with the stellar age population. So a reasonable question is, which of these two is the driver in this excess? So to answer that, we perform a partial correlation test accounting for the upper limits on the average population of our galaxies, on the stacks. And what we find is that when we examine the LXS, the X-ray luminosity excess and metallicity, and we fixed for the age indicator, the variance is lower, while when we do the opposite, the variance is higher. So that means that the stellar age seems to be the population of the stellar age of the populations in our stacks. It seems to be more strongly correlated with the X-ray luminosity excess that we measure. But it's very important to be sure that this excess that we observe is not contaminated by any other kind of contaminant. And one of these contaminants could be the background AGN. Because in our analysis, we measured all the X-ray emission within the D25 of a galaxy, it's possible to have photons from a background AGN. To calculate this contribution of background AGN, we calculated the expected flux from these sources for our stacks. And we found that the median contamination of our sample from background AGN emission is 70%. And that means that this number cannot access the observed excess that we cannot explain the observed excess that we measured. Another important thing here is that in this plot, where the color code is the background AGN contamination fraction, you can see that all the contamination is similar in all the stacks, which means that this excess that we observe here is not due to a significant contamination from background AGNs. Another possible contaminant could be the emission from low mass X-ray binaries, the contribution of these populations. So In order to quantify this contribution, we calculated the expected X-ray luminosity from these populations, and we did this analysis for both individual and stacks in the SFR stellar mass distance bins. And we find that the contribution from low mass X-ray binaries cannot explain the excess in lower star formation rate, since, as you can see, it's less than 10%. So no background agent contamination, no high contributions from low mass X-ray binaries, especially in the lower SFR regime where we expect to have more such systems. Another thing is the effect of the stochasticity. The question is, does this success has a physical origin, or is it a result of the stochastic sampling of the X-ray luminosity function of high mass X-ray binaries? As you may know, the number of expected high mass X-ray binaries, it strongly depends on the star formation rate of the galaxy. But small populations of high mass X-ray binaries, which means lower star formation rates, show stronger stochasticity effects. And in addition, we know that the shape of the X-ray luminosity function depends on the metallicity. You can see here an example of this metallicity evolution of the shape of the XLF. And at this plot here, we have very low metallicity, and the X-ray luminosity becomes more flatter, meaning that we expect more X-ray luminous sources in lower metallicity galaxies. To see this effect, to quantify this effect in our analysis, we simulated again the expected X-ray luminosity distribution due to the stochastic sampling of the high mass X-ray binaries X-ray luminosity function. And here, with the pink lines, here and here, you can see the 99.9 confidence interval of the X-ray, of the simulated X-ray luminosity distribution. And you see that the population of extreme X-ray luminous galaxies is still much higher than the 99.9% of this distribution. That means that the probability to observe these galaxies by stochastic sampling of the XLF is less than 0.05%. Another very interesting thing in this plot is that you can clearly see the effect of the metallicity in the X-ray output of the galaxies. The red line is the X-ray luminosity function of Mineo, who didn't account for the metallicity effect. And the yellow and pink line is the X-ray luminosity function from Limer, who accounted for this effect. And you can see that even in the lower SFRs, the X-ray output that we expect from Mineo is lower than the Limer. And this indicates the flattening in the XLF that we saw before. So stochastic sampling is not adequate to explain the most X-ray luminous galaxies that we observe in our sample. So another thing that it could be responsible for this excess is contributions from low luminosity agents. Although that we try to follow a very strict analysis for the defining of the sample of galaxies that we use by selecting the bona fide star-forming galaxies, still there is a possibility to have contributions from low luminosity agents. To answer this question, we perform the following exercise. Let's assume that all the X-ray emission that we measure in our sample is due to accretion onto a supermassive black hole. The question is, how powerful is this accretion? To answer that, by using the stellar mass of the galaxy in our sample, we calculated the expected mass of the black hole, and from there we calculated the Eddington luminosity. When we had the Eddington luminosity, we calculated the Eddington fraction And what we found is that the Eddington fraction of our sample, the galaxies in our sample, is typical of Seyfert-1 galaxies. And here you can see the distribution of the detections in our sample, color-coded by this Eddington fraction. Also, using the Eddington luminosity, we calculated the expected emission in the optical regime. And we found that this emission is very high. It's 3 times 10 to the 39 ergia per second. So, since we have so intense optical emission, we would expect that these galaxies should show AGN signatures in their optical spectra. But look, for the galaxies that we had available spectroscopic information, which are happens to be very high in the X-ray luminosity, their optical spectra has this form. And these optical spectra are characteristic, are typical spectra of star-forming galaxies. And not only that, these two are typical spectra of star-forming of galaxies that they have very intense star formation. So the answer is that no, this success is not due to low luminosity AGNs, since that even the higher, the most X-ray luminous galaxies spectroscopically are confirmed as star forming. Another possible contamination factor could be the tidal disruption events. So to calculate this in our sample, we utilize the TDE rate calculated for star-forming galaxies, and by using the sample of star-forming galaxies, the size of the sample of our sample, we calculated that we expect 0.3 TDEs per year. Now, since the eROS-1 scans the entire sky every 6 months, we expect that this number is much lower. So again, TDEs cannot explain this high X-ray luminosity excess. So what is this emission? The answer is that we find that there is a rare subpopulation of galaxies with very high specific star formation rates, lower metallicity, the color code here is the metallicity, and very young stellar populations. And this is also confirmed by their optical images. You can see how blue colors these galaxies have, and also by their spectra, which are typical star-forming spectra. So our populations, our subpopulations, we believe that it has a recent star formation episode, and the fact that we found that this population is, it shows the importance of large all-sky surveys, because eROSITA can find such rare and identify such rare galaxy populations. By having said that, I would like to come to my conclusions. In this talk, I present to you the results of the first X-ray unbiased all-sky survey of star-forming galaxies with eROSITA, and with the most updated star-forming galaxy sample, we updated the X-ray scaling relations between the LX and SFR and LX, SFR and metallicity. We also discovered the population of extremely X-ray luminous galaxies, and their star-forming nature is also confirmed by their optical spectra, and this is very important. We saw that the driver of this success is the high specific star formation rate, the lower metallicities, and the very young stellar populations of a subpopulation of this subpopulation of galaxies. And also that the stochasticity effects are very important. These results had very important implications for binary formation studies in low metallicity and high redshifts. And in order to manage to perform all this study, we have to base on the updated version of the Hecate catalog, which is very useful for all kinds of galaxy studies, and also the new activity diagnostic developed from Haralabos Daoutis, which is able to identify low luminosity AGN and extreme starbursts. Our paper have been submitted to ANA, and it's also available at archive since last week. So, thank you very much for your attention.
Thank you very much, Elias. This is very interesting and nice to see. Are there any questions? Yes, Nanda?
Thank you very much. Extremely interesting. I have a couple of questions from completely different fields, so from ignorance probably. So the first one is, so your luminosity excess is very interesting. I mean, at least you showed it as very interesting, even for somebody not in the field. So I guess this is so. But my question is, I suppose that it's true that the eROSITA data are very deep and the survey is very complete, but still in the past you had, I don't know, the XMMU survey or other kind of surveys that might have detected those same targets that you have. Can you confirm, I guess you tried to see whether those targets were observed by other instruments and if this sort of goes toward your luminosity, the excess or not?
Yes. First of all, the reason that we managed to find this population so high X-ray luminosity is the fact that eROSITA observes all the sky, while all the other studies observe small parts of the sky. Although that they go deeper than eROSITA, they are limited in a small part of the sky. One thing is this. The second thing is that indeed we tried to compare our fluxes, the fluxes that we calculate with our analysis, with archival data from Chandra, from XMM. And we found that there is a very nice one-to-one correlation within the error bars, obviously. But this analysis for the available galaxies that we found confirm that there is the two fluxes by us and by the other surveys can be compared. And the excess is not due to technicalities and instrumental effects or all this. I can show you the plot if you want.
I trust that. I have another question. You showed a certain point or stack spectrum.
My stack spectrum, yes.
Page 25. Can that be like this? Yes, that one. So I was wondering, so I guess because at higher energies, it's very, maybe those are different sources, so I understand. And there is a line, I guess it's a calibration line, right? At 2.1, I suppose.
Where?
So this deep.
This thing.
On the left, I guess it's a calibration of your Z.
Yeah, probably, yeah. Yeah. It's not a line.
Yeah. So my question is, do you think that the discrepancy at higher energies that at least seems by eye in the spectrum can affect your general flux determination?
You mean this?
Yes.
I would like to clarify something here.
Yes.
The fit or the X-ray fit has been performed in the most sensitive energy band of the eROSITA, which is from 2.3 to 5. So all what you see here is an extrapolation of the baseline fit. It's not the actual fit on this data. Because here we go up to 8 kV.
Yes, but it seems, I don't know, maybe it just depends on the binning. So it might be that it's not true. But it seems that between 2.1, between the calibration line and 5, you have a general stability.
I think that this can be answered by the residuals, but the residuals seems to not be so important. Here, you can see it's 0.0001.
Yeah, so, maybe if you bin it more, you will see if there is or not.
The plot here is, you mean plot, binning the data, the counts in the spec. Yes, it's an adaptive binning. I don't remember exactly the numbers now of the binning, but we don't have the same binning in each energy here. But okay, yeah, I could check.
No, I was just, I mean, whether this can or not.
No, I really
your
don't
flux
believe.
determination.
Yeah, I really don't believe that it could be the excess that we observed. It could be this because of this.
Thank you.
Any other questions? Yes, Aldo?
Thanks. I'm even further away from the field than Nanda. My question will be here. So actually, if you go back one more to the 24, so one previous, okay. So in general, I'm wondering, what do you mean, or what do people mean when they talk about the metallicity of the galaxy, right? Because the galaxy is a complex system, right? So what does it mean, metallicity?
It's okay. When we talk about metallicity, maybe someone can understand the metallicity of the star, of a star. But in our case, we don't talk about this. We talk about the gas phase metallicity. So the metals that are in the entire galaxy that we measure, that we study. So when we say about gas phase metallicity, we mean the amount of metals that we have in the galaxy, in the entire galaxy.
So you have let's say, a spectrum of a galaxy, so you're measuring some sort of average.
Yes, it's exactly. It's like measuring the spectrum of a galaxy. You have contributions from the stellar populations, from the gas. If there is an AGN, you also have contributions in the final spectrum. So yes, it's the average gas phase metallicity of all the galaxies that we measure.
Or if I may say something here, because the Higgs division one, also sometimes, in intergalactic astrophysics, you don't have the luxury to get observations, wide observational data, of galaxies or nearby galaxies. So some of these are coming from nuclear spectra. So you may have a little bit biased metallicities, they be a little bit higher metallicities than the average of the galaxy. So it depends on what observation you use. However, these are the kinds of the observations that have been used before to create the mass metallicity relations for galaxies. For example, the SS data are kind of standards that they have identified what are these biases. So maybe the numbers, the normalization might change a little bit because of your definition of what is the metallicity of where you get extracted from the galaxy. But in general, you expect to see all the trends that we see in interstellar astrophysics or in X-ray binaries with this nuclear spectra.
And also, if we don't, if we are not limited in the nearby galaxies that are extended, and you have more distant galaxies, then the entire galaxy falls into the slit. So what you measure is the average of the entire galaxy. While if it's nearby, it's like I don't know where it had the. Yeah, if this galaxy is nearby, you can put the slit here in the core, in the nucleus, and measure what's happening there. But if the galaxies are more distant, as in our case, we don't have this problem.
Yes, because I'm wondering, when you have, again, in slide 24, right? So you have on the y-axis on the right-hand side plot, say 3, even 4 orders of magnitude different star formation rate, right? So this is going to affect the spectrum of the star, right?
Mm-hmm.
If you are really measuring the same thing, right, in both cases, so if you have a galaxy with star formation 10 or 10⁻�3,
mm-hmm.
if what you call metallicity is really the same thing in both cases, right? So
it's the same thing.
If you have strong star formation, you have very young population, your spectrum might be dominated by a relatively small amount of stars in the whole galaxy, simply because they are so luminous, the very young massive. It seems such a nice correlation between the mass and the metallicity there.
Of course, we expect this correlation with mass and metallicity, right? It's the mass-metallicity relation. So higher masses, higher metallicity.
Okay.
And this is because of the evolution of the stellar populations in the galaxy.
Yeah, this is the main sequence. So star formation is related to stellar mass, and then you have the mass metallicity relation. So they're also, both things. Yeah. And especially,
Again, as if from ignorance. And do you see the same with the supernova rate?
With that?
So if you see this correlation the same with the supernova rate, because I guess this means that you have more supernovae, you are higher metallicity. So if you correlate with the supernova rates. total,
I would like to
should have
check
it,
it,
right?
but I haven't checked it.
Okay, just if you need.
Maria?
One determines supernova rate
Yeah.
for individual galaxy.
But
Well, for the
True.
kind of galaxy, right? You know the star formation, you know the mass. We
you
have so
mean,
many supernovae, so we can,
the expected number of,
depending on the mass of the galaxy, how many supernova you expect from observation.
to derive it, because this is
Yeah,
observation,
right,
right?
we not observe them one by one. no,
Ah,
no.
all
Uh,
the, yeah, so that depends strongly on the star formation history, so. And so you take an assumption here for the star formation history, so you kind of lose the effects and the scatter and all the interesting things that it's gonna depend on the age. So you
There
have,
is a strong variation in the
Yeah.
formation history going parallel, going between the red line and the blue line. There is a strong variation in the formation history. So one would expect a higher supernova rate closer to the blue line and a lower supernova rate to the red line. But also a variation as to higher mass.
Yeah.
With higher mass, you have more like. So it's a very complex.
any other questions?
Yeah, one more.
yeah,
So if in this vertical axis, instead of star formation rate, you will use the specific star formation rate. The whole trend disappears, right? So you just, would you just get something flat, and then that will also eliminate the trend between the with the metallicity. So I'm
in
just
this
trying to
plot,
understand if star formation rate depends on metallicity or not, right? So if we would do the specific here on the y-axis.
on the Y, the specific is this
I'm
diagonal.
looking at the other.
Yeah. So if I use the specific star formation rate, no, it would still have a metallicity dependence. This,
Vertically,
Well, it's 4 orders of magnitude on both axes, right? So if I divide the star formation rate by the mass of the galaxy, that would give me a flat
yeah,
line.
but the color code would remain the same.
Yeah,
So,
but I will get. a flat
ah,
line.
yes,
So there would be no correlation between metallicity and specific star formation rate. So one could conclude or not that the star formation rate doesn't depend on metallicity.
mm,
I mean, the specific star formation.
I'm not sure how this plot would like, but I would expect that there is dependence of the metallicity on the specific star formation rate. Yes, I would expect that for higher metallicity, for higher specific star formation rates that would have more intense star formation rate, the metallicity would be lower because we have younger stellar populations in the galaxy.
yeah, but this is where you have also lower stellar mass, the galaxy, because it's lower. So when you divide, you expect that this trend is gonna move. So it's like taking this band, rotating it here, because you
Yeah.
divide by the star formation rate. So the effect you want to see is that there is lower or higher metallicity towards this direction.
Okay.
So, of course, the sample is not big enough to answer with these galaxies, but in the general population, you can. I mean, I have tried that for the Hecate one, for example, at some point. So there's not enough sample. Maybe now you can see better because you have the new diagnostics. So you can try to see that.
Yeah.
But generally, you expect the metal, the mass to be the dominant factor, right?
Yeah, well, the mass is part of the dominant factor because most of the metallicities are coming from the mass metallicity relation, so there is a correlation. But maybe you can check that from the LX specific star formation rate plot where you have color coded the metallicity. Yeah. No, no, LX specific star formation, the limit plot.
I don't know if I have
Yes, you
the
have this with
color coded with metallicity. Maybe I don't have it here.
Because that could, be a way to see that.
No, I don't have it. No. No. No, I don't have it.
We just need to make it and see,
Yeah.
how it looks.
Yeah, that's probably a good paper.
Yeah.
Yeah, true. Good post.
So, any further questions? Maybe we'll have the time for just the last one. Yes,
Just
Nanda?
for in the future, and what's next? So are you waiting for more eROSITA data to go deeper, or
Exactly.
or you can help on having more sources to start with, and then search for the increase?
For the moment, the next plan is to rerun this analysis with the eROSITA data. And the reason is that, first of all, eROS data from the fourth scan would go deeper, so the signal will be higher. And with that new generation of data, sorry. Here, we will manage to recover a population of that now is upper limits. We recover it and we have detections. And that you can imagine that it will be very useful because we will have a much larger population of galaxies, of star-forming galaxies, and much more detections. And so the next plan is to rerun this analysis to see what we find, how the scaling relations change. And we are also planning to, depending on the availability of galaxies in eROS-4, to study to go one step further to X-ray luminosity functions, like the linear one that I saw. And yes, I think that the two basic next steps is this one. And again, trying to study correlations. Another thing that I would like to check is, first of all, to see if there are better age indicators that can trace much younger populations, because now we have the Helium-1, but ideally, I would like to have the Helium-2 line to Helium-1, because Helium-2 is from very, very young stars. And another thing that I'm very interested to do, and I'm planning to do it as soon as possible, is to, as you see, we find that there is no, let's go back to the best picture. Okay, here. We find that there is a correlation of the scatter with the star formation rate. In our fits, in this work, we model this correlation as a linear function. We model the intrinsic scatter as linear function, where here we have it's a normal distribution with mean in the zero and standard deviation this. But the question is, why this? So what I would like to do is to find a way to parameterize this scatter and update the assumptions in the fit to see how the scatter really depends on the star formation rate.
So Elias, this yellow band here,
Is the 1 sigma
so
scatter?
it's not the uncertainty on the parameters of the fit.
No.
It's a result of what is the intrinsic scatter because of the.
And for that
galaxies
reason,
we
you
have there.
see that it's becoming larger, going to lower star formation rate, because there is this dependence on the SFR.
Because you
But it goes
Right.
linearly. It's not, maybe it's not the truth. So yeah. And we have the machinery to do that. We know how to do it, but we have to do it. We have to find time to do it. Yes.
Nice. So I think we should finish now. We are over the hour. Thank you very much again, Elias.
Thank you very much. Thank you for giving me the opportunity to present my work. It's very nice to know. I realized that I like to interact and talk with people. And when I was younger, I was very shy giving talks, and now it's my first time that giving talk like seminar. So I think that I like it.
And started PhDs during
So
COVID.
maybe
COVID PhD students, right?
yes, I'm COVID.
Okay, so
So I will try to visit you again with eROSITA updates.
Yes, please.
Alba, it's okay. We can stop recording. Thank you very much.
Thank you.